Pause with the fans.
Petrochemical feedstock. The refinery product are naphtha, gas oil and catalytic cracker gases. In oil industry, gasoline fraction. In petrochemical industry, naphtha is the petroleum fraction that boils between 20 to 80 degrees Celsius. Naphtha mix of alkane, cycloalkane and aromatic hydrocarbon. Gas oil are mix of have the same component but with higher molecular weight. Refining crude oil. Crude oil is a complex mixture of hydrocarbons, and to separate the constituents, we apply the method of fractional distillation. It is a process whereby petroleum is separated into different portions called fraction. Each fraction contains several compounds, all of which fall within a certain boiling point range. This fraction can be differentiated from one another by their different texture, color, odor, volatility, and their relative case of ignition and burning.
Earth. If you look closer, you'll see that a whole other world exists beneath the surface of land and sea. Layer after layer of rock structures go deep into the Earth's crust, mile after mile, and trapped within these structures, along with other liquids and solids, you'll often find deposits of oil and natural gas, the world's two most important sources of energy. These famous fuels are in constant demand because they make the world go round, day in and day out. So how do you find something that's completely hidden beneath the Earth's surface? It's a mystery that people in the oil and gas industry are always trying to solve, and for very good reason. Drilling for hydrocarbons is expensive. And before they spend money on equipment and crews, exploration and production companies need a reliable strategy for pinpointing where to drill. Geoscientists have a secret weapon called seismic exploration, and it involves sending acoustic energy, which takes the form of wavelets, into the ground to get a sound picture beneath the surface. It's complicated, so let's start with the analogy of bats. Bats can't see very well, so they send out little waves of sound that bounce off of objects and then go back to their ears. It's called sonar. It gives them what you might call a sound picture of their world. That's a good example of how nature already uses a form of seismic acoustic imaging to locate objects. Doctors also use it for ultrasound imaging. Geoscientists use man-made tools to make the sound wavelets, listen to them, and then record them. When you want to know if oil and gas deposits are in a particular area, geophysical companies bring large trucks that have big vibrators on them. Most of the time, this is what generates the acoustic energy or vibration. They use geophones, or very sensitive seismic microphones, to hear the reflected sounds, but sometimes they set off small buried charges. They set many geophones on the ground in a line, and they are attached to a recorder inside another truck. The vibrators send thousands of wavelets down into all the different layers of the Earth. Some of the wavelets bounce off of the boundaries between the rocks below the surface and are reflected back to the geophones that are waiting to record them. Each geophone along the cable sends the received wavelets to the recording truck where they're recorded and stored. Here's what seismic looks like after it's been recorded. Basically, it's a bunch of squiggles. There are still a few more steps to go before it begins to look like an actual picture of the Earth's interior. Right now, the data is still in its raw form. To get a picture that actually looks like the Earth beneath us, the data has to be processed. It takes a large supercomputing PC cluster to process the seismic data. These computers go through all the different traces made by the wavelets and filter out everything we don't need, such as vibrations made by a tractor in a field nearby. Using really amazing computer applications and working on state-of-the-art workstations, geoscientists can see the seismic data translated into a 3D picture. You might be thinking, I don't see any oil and gas there. But believe it or not, geoscientists can look at this processed data with their trained eyes and make an informed decision about whether or not oil and gas deposits are in the geologic structures. Seismic data leads to a high percentage of drilling success with less risk to the environment. And in a world where the demand for oil and gas is increasing faster than the supply, good seismic information will lead to more affordable energy.
Vertical or directional drilling is conducted to assess potential resource reservoir deep beneath the Earth's surface. Vertical drilling is straightforward, aiming directly downward, while directional drilling allows for angle path to reach difficult location or multiple targets from a single site. Directional drilling is an advanced method that enables the engineer to steer the drill bit along a precise path. This technique is essential for reaching targets that cannot be accessed by vertical drilling alone. For example, reservoir located under city's sensitive environment or offshore platform can be tapped without disturbing the surface above. The process involves real-time monitoring and adjustment. Engineers use advanced software and sensors to guide the drill bit, ensure it stays on the desired trajectory. Directional drilling also allows for the creation of multiple well paths. From a single location, multiple wells can extend outward, minimizing the environment footprint while maximizing resource recovery. For the core sampling, the cuttings, fragments of rock crushed by the drill bit are brought back to the surface by the mud. To obtain information on the characteristics of the rock being drilled, a core sample are taken. The drill is replaced by a hollow tool called a core sampler, which extracts a cylindrical sample of several meters of rock. This core supplies data on the nature of the rock, the inclination of the layers, the structure, permeability, porosity, fluid content, and fossil present. For the well evaluation, logging process. After having drilled a few hundred of meters, the explorer and driller undertake measurements down the whole core logging by lowering electronic tools into the well to measure the physical parameter of the rock being drilled. This measure validate or invalidate or make more precise the hypothesis put forward earlier about the rock and the fluid that they contained. The log engineer is responsible for the analysis of the result of the various loggings. The sides of the well are then reinforced by steel tubes screwed end to end. These tubes called casing are cemented into the ground. They isolate the various layers and counter the test. When hydrocarbons are found and if the pressure is sufficient to allow them to come to the surface naturally, the driller do a flow check. The oil is allowed to come to the surface during several hours or several days through a calibrated hole. The quantity recovered is measured as the change in pressure at the bottom of the well. In this way, a little more knowledge is gained about probably productivity of the field. If the field seems promising, the exploration team ends the first discovery well and goes on to drill a second. Finally, an economic feasibility studies determine whether extracting the resource is financially available. Cost of extraction, processing, and market conditions are all considered. Gas plant processing. The onshore processing facilities (OPF) separate, compress, and feed hydrocarbon from offshore platform for further processing and transportation. Raw hydrocarbon, including natural gas, crude oil, water, and ethylene glycol, arrive at the OPF, where a three-phase separator divides the mix into methane, condensate, and water, with ethylene glycol purified and returned to the platform. The OPF is eco-friendly, generating electricity using natural gas to power itself and the offshore platform. To address declining reservoir pressure over time, a compression station is integrated to maintain the required pressure for transport. The final product, oil blend with condensate and purified natural gas with over 90% methane, arch via pipelines, ensure seamless integration in the hydrocarbon production and transport chain.
Producers dehydrate gas by removing the water from it. All three sectors of the oil and gas industry use dehydration, including upstream at individual well locations, midstream at gathering stations and delivery points, and downstream at processing plants. To take the water out of natural gas, producers use a liquid called triethylene glycol, also known as TEG. When gas comes into contact with the triethylene glycol, the water vapors entrained in the gas are absorbed in the TEG. In effect, the glycol soaks up the water. The glycol is then removed from the gas stream for processing so that it can be purified and reused. There is a lot of equipment needed for the dehydration process. Natural gas only travels through the inlet scrubber and the contactor tower. On some sites, these two vessels are combined into one unit. All the other equipment is used to regenerate the glycol. As the glycol moves through the contactor tower, it absorbs the moisture from the natural gas. The glycol then flows into a three-phase flash separator which separates the rich glycol from the contaminants, lubrication oil, free water, and condensate. The contaminated liquids exit and are removed to storage tanks, while the glycol then goes to the reboiler. The reboiler's distillation process removes the water contained in the wet glycol. This allows the water to be boiled off and the glycol to be distilled to an appropriate level of purity so that it can be reused. The water flashes off as steam, but the glycol remains in the reboiler. Glycol in this stage is now referred to as lean or dry glycol.
The purification stage in gas plant processing involves several critical steps to remove contaminants and meet gas specifications. So the process begins with hydrogen sulfide removal, typically using amine absorption system. This is where sour gas flows through an absorption tower while amine solution captures the hydrogen sulfide, reducing its content to less than 4 ppm. Then the carbon dioxide removal often occurs simultaneously using the same amine systems, though membrane separation or molecular sieve can also be used that targeting carbon dioxide reduction to 1 until 2% or lower to prevent pipeline corrosion. Mercury removal follows utilizing activated carbon beds or specialized molecular sieve to reduce mercury content below 0.01 nm3, which is crucial for protecting downstream aluminium heat exchangers and meeting environmental standards. So this comprehensive purification process ensures the gas meets pipeline specifications, protects equipment, prevents corrosions, and hydrate formations, and lastly maintain environmental compliance and process safety standards.
The NGL process of gas treatment is an important process for the production of natural gas liquids, as it ensures that the natural gas is of the highest quality. This process involves the removal of impurities such as water, liquid hydrocarbons, and other heavy hydrocarbons from natural gas. In order to maximize the efficiency of the process, it is important that the natural gas is properly treated before it is sent to the NGL plant. The first step in the process is typically the removal of water from the natural gas stream. One of the significant challenges of the NGL fractionation process is the need for processing plants to separate NGL from natural gas. NGL recovery is a process whereby natural gas liquids are recovered from natural gas and separated into individual components. The process involves the separation of hydrocarbons, such as ethane, propane, butane, and pentane, from natural gas. This separation is accomplished through a series of stages, each designed to remove one or more of the components. At the first stage, the natural gas is passed through a separator that removes heavier hydrocarbons. This is known as the primary stage of NGL recovery. The separator is a pressure vessel where the natural gas is passed through a series of baffles or trays. The heavier hydrocarbons, such as propane and butane, are allowed to settle to the bottom of the vessel and are collected for further separation. The second stage of NGL recovery is the fractionation stage. In this stage, the heavier hydrocarbons are separated into their individual components. The process involves the passage of the hydrocarbons through a series of towers or columns. The heavier components, such as propane and butane, are allowed to settle to the bottom of the tower, while the lighter ones, such as ethane, are directed to the top. The hydrocarbons are then collected and stored in separate tanks. The final stage of NGL recovery is the stabilization stage. This process involves the cooling and condensation of the hydrocarbons. The hydrocarbons are passed through a series of chillers in order to reduce their temperature and condense them into liquids. This process is done in order to ensure that the hydrocarbons are compatible with the storage tanks and that they do not vaporize. NGL recovery enables the separation of natural gas into its individual components. One of the significant steps in the NGL fractionation process is using an adequate filtration system. The filtration system is essential as it helps to remove any impurities in the NGL. Impurities can cause operational problems and reduce the quality of the NGL, leading to a decrease in their value. The filtration system used in the NGL fractionation process should be of high quality and designed to handle the specific impurities present in the NGL. The system should be properly maintained to ensure it functions optimally.
So in this part, I will explain about refinery process.
The video outline for this part is crude oil reception, distillation, and conversion process. So the requirement for storage tank in refineries are design, safety, operations, compliance, and features it required for the safety in the refinery. For desalting process, which is remove salt, water and solid to prevent corrosion, fouling and catalyst poisoning, it has several steps for this desalting process, which is first mixing, second heating, third electrostatic separation, fourth water removal. So desalting has two types, which is single stage desalting and second two-stage desalting.
Refining begins with a process called distilling. After oil is superheated, it becomes vapor. The vapor is fed into the distillation unit. As it rises and cools, the vapor turns back into a liquid. Using stacks of trays, the liquid is easily collected and separated by weight. The lighter and medium weight liquids require less processing before they're ready to be used in cars and trucks. The heavier liquids need more processing to become useful.
For distillation, it has three types, which is atmospheric distillation, with initial separation of crude oil into broad fraction in atmospheric pressure. Second, vacuum distillation, which is process heavier fraction under low pressure to avoid thermal cracking. Third, fractional distillation, which is separate mixture into components with different boiling point that occur at atmospheric or reduced pressure.
A process called cracking is used to maximize the usefulness of heavy oil. Heavy oil has long strings of carbon and hydrogen molecules. Using a catalyst, these molecules can be broken into smaller chains, transforming the heavy oil into lighter, more valuable fluids.
Cracking process. It convert less useful heavy hydrocarbon into lighter and more marketable product. It enhances refinery profitability by increasing the yield of high demand fuel. Cracking has three types, which is thermal cracking, catalytic cracking, and hydrocracking. Thermal cracking uses heat and pressure to break hydrocarbon bond, while catalytic cracking uses a catalyst to promote breaking of hydrocarbon chain. Hydrocracking is combined cracking with hydrogenation.
Reforming is a process that increases the amount of gasoline produced from crude oil. One of the products separated in the distilling process is a liquid called naphtha. The number of carbon atoms in naphtha is about the same as the number found in gasoline, but their structure is more complex. Reforming rearranges the naphtha molecule, turning it into a usable gasoline-like molecule.
Reforming technique. Reforming techniques are chemical process used in refinery to improve the quality of hydrocarbon by modifying their molecular structure. This technique primarily increase the number of gasoline and produce valuable byproduct like hydrogen. Reforming has three types, which is catalytic, steam, and thermal. The application of reforming is improving gasoline quality, producing hydrogen for refinery process like hydrocracking, and generating petrochemical feedstock such as benzene and
Hello and
toluene.
hi everyone. Today I will present about overview of some critical process involved in the oil and gas industry. This process include the treatment process, petrochemical production and cracking process. So for the first one is treating. Hydrotreating is used to remove impurities such as sulfur, nitrogen and metals from crude oil and natural gas. Sulfur removal is particularly important because it prevents the production of sulfur oxide, which is harmful pollutants. Also for the metal and nitrogen compound extraction, metal and nitrogen compounds are extracted to prevent fouling and poisoning of catalysts used in later refining process. This ensures that efficiency and longevity of the equipment and process downstream. The objective of the treatment process is to prepare a clean feedstock suitable for further refining and chemical production. So this is the chemical reaction involved. It's about basic feedstock preparation. For the first one is naphtha extraction. Naphtha extraction is a light hydrocarbon mixture obtained from crude oil distillation. It is used as a primary feedstock in produced chemicals like ethylene and propylene through cracking. For ethane and propane selection, ethane and propane are separated from natural gas liquid as known as NGL. They are key feedstock for producing ethylene and propylene through cracking process. For the initial molecule process, separation. This step involves separating hydrocarbon into distinct fractions based on their boiling point. It allows for precise utilization in various applications such as fuel production or chemical synthesis. For feedstock preparation, the feedstock undergo preparation to make the specification required for the next stage such as cracking or reforming. Proper preparation ensures optimal performance in downstream chemical production. So this is the how production of stream chemical production. Next is about cracking process. In this topic, I will explain about steam cracking and catalytic cracking. Steam cracking, in this process, hydrocarbons like ethane, propane or naphtha are heated in the presence of steam. This breaks down the molecule into smaller ones such as ethylene and propylene, which are essential for producing plastic. Catalytic cracking is used as a catalyst to break down heavier hydrocarbons into lighter ones like gasoline, diesel, and olefins. This process is highly efficient and widely used in modern refineries. For the molecule transformation and building block generation, the smaller molecules obtained from cracking serve as building block for creating a variety of products, from fuels to polymers. This step is crucial in meeting the global demand for petrochemical and energy. So this is video about experiment of cracking process that we can do in laboratory. In conclusion, the oil and gas industry involves a series of sophisticated processes from treatment to petrochemical production and cracking to transform raw hydrocarbon into valuable product. Each step is interconnected and essential in ensuring the efficient use of our natural resources.
Chemical conversion. Polymerization is a process that combines light olefins like propylene and butylene to create larger molecules. The process begins by pre-treating the olefin feedstock to remove sulfur and impurities. A catalyst such as phosphoric acid or kieselguhr is then used to facilitate the reaction. The process is carried out under high pressure, typically between 30 to 75 bars or 400 to 1100 psi, and at temperatures ranging from 175 to 230 degrees Celsius or 350 to 450 Fahrenheit. Cold feedstock is injected into the reactor to control its pressure. The result is the production of higher olefins with high octane numbers, which can be used as gasoline blending stocks. Alkylation is a process that produces alkylate, a high-octane fuel compound for gasoline. In this process, a light hydrocarbon such as polypropylene or butylene is combined with isobutane. A catalyst like sulfuric or hydrofluoric acid is used to facilitate the reaction, producing a mixture of heavier hydrocarbons. The liquid fraction is then extracted as alkylate. The resulting alkylate is a mix of branch hydrocarbons with a motor octane number MON of 90 to 95 and a research octane number RON of 93 to 98. It plays an essential role in motor and aviation gasoline. Isomerization is a process that converts straight-chain hydrocarbons into branch-chain hydrocarbons, which have better performance characteristics and higher octane ratings. The process improves octane by enhancing naphtha octane rating, which helps reduce engine knocking. It also helps clean fuel specification by enabling the production of low benzene gasoline. Additionally, isomerization produces high-value products used for jet fuel and petrochemical feedstocks. The process typically uses a catalyst such as zeolite or platinum under high temperature and pressure conditions to produce branch-chain hydrocarbons that are essential for high-octane gasoline. Specific compound creation involves producing specific chemical compounds such as high-value petrochemicals or pharmaceuticals from raw materials or intermediate products. The process starts with raw material preparation where base hydrocarbons or chemicals like ethylene, propylene, benzene or toluene are isolated. Next, chemical reactions such as hydrogenation, oxidation or Friedel-Kauf alkylation are used to create the desired compounds. Finally, the product is purified and isolated, making it ready for further use in product development, including plastics, synthetic rubber, or pharmaceuticals. Product development. Plastic manufacturing starts with polymerization, where hydrocarbons or monomers are chemically bonded to form polymers. Next, the polymer is melted and molded into the desired shape through molding or extrusion, creating films, fibers, or molded components. Finally, in the post-processing stage, the product is cooled, cut, and processed into its final form. Synthetic rubber production begins with the preparation of monomers, where raw materials like butadiene or styrene are purified. Next, in the polymerization stage, methods such as emulsion polymerization are used to polymerize the monomers into rubber. Finally, the polymerized rubber undergoes curing or vulcanization using sulfur to enhance its elasticity and durability. Pharmaceutical intermediates are chemicals used as precursors in drug formulations. The process starts with the synthesis of intermediates, where chemical reactions like Friedel-Kauf alkylation, hydrogenation, or esterification are used to create compounds such as active pharmaceutical ingredients. API, or other intermediate compounds. Next, the intermediates undergo purification using techniques like recrystallization, distillation, or chromatography. Finally, these purified intermediates are used in the formulation of the final pharmaceutical products. Specialized chemical synthesis involves the creation of specific compounds with specialized use such as in agrochemicals, electronics, or specialty polymers. Such involves raw material selection where based on the target compounds such as electronic materials, high-performance polymers, appropriate raw materials are selected. Next, reaction steps where various chemical reactions are employed such as acidification, hydrolysis, oxidation, or reduction to be complex molecular structures. Finally, purification and characterization, where the synthesized product is verified and characterized to ensure it meets the required specifications for use in its intended applications. In conclusion, oil and gas production covers interconnected stage from exploration to petrochemical synthesis, each requiring precision and advanced technology. This exploration highlighted the critical role of innovation in optimization, efficiency, and ensuring safety. The main challenge is balancing energy demand with sustainability by refining these processes and embracing new technologies. The industry can meet global energy needs while ensuring a more sustainable future.
That's all from us. Thank you for watching. Bye. Bye-bye.